My name is Thomas Baker, and I'm here today with two members of my group, Aaron Dayton and Kiana Gallagher. We're going to talk today about some software research that we use in the group, which we've been getting more and more emails about. So it seemed time to put together the final version 1 release of this. So I'll start. And what we're going to talk today about are some basic features of the library and some of the algorithmic perspectives that we have in the context of how we design this from just the base Julia library. Everything that you're going to see here today is only Julia, 100% Julia, in fact. And so hopefully this is a conversation starter with people here about design principles and things like that. So DMRjulia is a software package to model quantum physics. Basically at the level of strongly correlated phenomena. So it has a kind of a long history. I started this back in 2016, and then through a series of positions, which I'm grateful for the funding for, I was able to put together something that really reached the goals of Julia and being something that is simple, lightweight, and fast, and that also is as fast as lower level implementations of the same algorithms, although that was not the most straightforward thing. So one of the primary methods in this field is called the density matrix renormalization group. And what we do is we separate some big vector that is generally exponentially sized into a site-by-site decomposition in the basis of entanglement. It turns out that this is a good ansatz because physically relevant systems have what are called a local interaction, which means that you can essentially perform this decomposition and then you get a much more favorable scaling for the problem without losing too much accuracy. So there's this diagrammatic notation, which is to say that we can envision the large vector that we have as being some sort of tensor. And when we perform the decomposition, then we get a set of tensors that are represented on the bottom, and each of the legs is signifies one of the indices on the tensor. So a tensor of rank 2 is shown on the left with 2 indices coming off of it. And the entire idea behind the physics of this, and if you're not familiar, there's 2 references here, one of them in French and one of them in English. If you want to perform some sort of decomposition on a wave function in quantum mechanics, then you can perform this operation and realize that the decomposition in the space of density matrices is just the singular value decomposition. And that means that you're able to convert all of your operations down to matrix operations. So there's a very nice feature of Julia that it already has BLAS implementations of matrix operations, so we just leverage those in order to get ground state properties out of this system. If you pay attention in the back half of a physics curriculum, then you start to deal with things like density matrices and like entanglement. And if you know a little bit about the structure of quantum physics problems, you realize that density matrices, in terms of their natural orbitals, or the diagonal basis, the occupational weights of the density matrix will drop off very quickly. And so what this means is that any student that is entering this area typically will only get to this information in the later years of their undergrad, and maybe not ever. It involves a lot of computation. It involves a lot of things that you don't get to encounter until very late going. And then when you do see them in the context of thermodynamics or quantum mechanics, it's typically not emphasized in the same way that would make it useful in order to start working in a research group, which means that having code that is very easy to use, that students can have a very quick uptake time, and that they can essentially jump into research means that it's the difference between being productive in a research environment and not being productive in a research environment. So Julia was a very natural choice for this. During one of my postdocs, I had the supervisor went to another university, and I was left with 6 students who had to do this. And it became very quickly very obvious that existing software packages that I'd worked on and that were out there, and existing reference literature was not sufficient to train students up to where they need to be in order to do this. So that might have just been because of the institutional program that was there. It wasn't sort of geared into this area, and that's fine. Maybe that's happening to someone out there. But the tools that have been developed here, the students have a much more rapid entry into the field on the time order of a couple of weeks in order to figure out what's going on. So it's been very beneficial, and now that I'm getting more emails from people out there that are apparently taking interest in this, I thought it was a good time to kind of go public with it. So let's talk a little bit about how you set up some of the basic tensor network constructs in the library. One of them that is the most basic one is called the matrix product state. It's modeled off the Aflac-Kennedy-Lieb-Tasaki state. And it's very good at capturing systems that have very short range entanglement. In the library, we have a very straightforward setup. So you can see that to actually start to run an algorithm, you maybe only need 7 lines of code. And if you want to run something that imposes quantum number symmetries, which can add a level of sparsity to the tensor networks, then this is only another couple of lines in order to do this. So very easy to kind of take something that's in the literature and then point to functions that are in the library, and then actually have the student just sort of say, go sentence by sentence of some algorithm that is going on in the literature, and then program everything that goes through. Now, if that's the wave function in quantum mechanics, you also have an operator. So here's a side-by-side decomposition of a matrix product of an operator, which is called a matrix product operator. Not as fancy as the matrix product state. And we have a nice auto MPO feature, which has been known in the community for a while, but it essentially allows you to write Hamiltonians as though you would be reading them in a paper. You can also extend this to 2-dimensional matrix product operators. So if you wanted to run a square lattice with arbitrary connections, then it would be able to construct the MPO for you. Obviously, the wave function ansatzes that we use here are much better for things that have smaller range interactions. But nonetheless, you can also extend this to quantum chemistry, and then you just get the same sort of structure here for a quantum chemistry Hamiltonian with a 1 and a 2-body interaction. The point is that you can just read something in a paper and then implement it in the code right away. We've also extended, and this is coming in the pending version 1 release of the library, to the 2-dimensional generalization of this. And this will work for any graph. You just need to supply the correct near neighbor table. But as you can see, to actually optimize this structure, in a lot of codes, they really bend over backwards to really make it efficient, I would say, and to get everything. We have it to a point where we have very little overhead on the actual optimization, and you can see that it's only a couple of lines. So a lot of the old literature in this field was written with a different purpose than educating new students, which is fine. It was really good work, and it really opened up a lot of possibilities. But having some code that actually makes everything compact like this is very beneficial for a research group. There's also this other graph ansatz called the multi-scale entanglement renormalization ansatz, and you can see our code is very, very short here. I haven't kept up with what other libraries are doing, but to do this in 12 lines is rather good. And it uses some concepts from graph theory that make this much easier in order to implement and to get people going on actually computing with these things. And I should mention that it's not just binary Mera that can be implemented here. That function to make the Mera net will handle any Mera graph that is in the literature. So it's quite a general function, and a lot of thought has gone into exactly how to design these things so that it's very general. We also have a variety of classical tensor networks that are implemented in the library. I think everybody knows about TRG that's in the field. That's the one on the left. It's just some decimation of a square lattice, although it can be extended to a Kagame lattice and a hexagonal lattice and a triangular lattice and a probably missing one. And then there's also the tensor network renormalization, which is another algorithm that is kind of using disentanglers to sparsify the problem in a slightly different way. All of these things are very small code bases. The student that is not here today, he was able to do this over the course of a couple of months, but basically implement an entire library of these classical tensor network algorithms into the library. And so we're hoping that this will be at least some sort of benchmark for future algorithms that may be made in this field. In order to download DMRjulia, it's a very simple procedure. The GIF that we have here is not sped up or slowed down. It's we're just typing very slowly. But it's 100% Julia, which means that it downloads very, very quickly. So there's no dependencies on anything. In the version 1, we are making a last-minute decision coming up here soon as to whether we include the OpenCL, so there will be some tiny amount of additional code that is there. But it downloads in a snap. You can start running it very easily, and it's as fast as lower-level implementation. So we sort of achieved the Julia ideal here. So in terms of a few design points, this code has existed through several versions of the Julia language so far, And we're just waiting for version 1.11 to release version 1 formally, because we like some of the features that are coming out. But this essentially rewrites many of the Julia functions. So that 10 pack, or the tensor pack that we were showing on a couple of the slides, that's essentially a replacement of linear algebra, because you need to have a slightly better way to access the tensor objects without introducing a type instability into it. And the thing that I have found that has worked, and if somebody has a better way to do this, this would be great, because then I could just use the base library a little bit more, was just to avoid the garbage collector. And that's largely the reason why everything is so fast. If anybody has any experience on GPUs, the status of parallelization in Julia at this point, some of the linear algebra functions and maybe the garbage collector, and I'll add one from this morning. If anyone has any experience on the RISC-V implementation of Julia, this would be a real treat to have some conversation with people about this. So in the next part of the talk, the two students that are in my group are going to take it and talk about some kind of externally facing features that are going to come out in this new functionality called DMRjulia that we're going to do. So go ahead.
Okay. So hi everyone, I'm Aaron.
And I'm Kiana.
And we're here to talk about a offshoot of Dr. Baker's project called DMRjulia. It is a website that will be releasing soon to allow users to very easily use some of these functions even without much coding knowledge. Mostly all built in Julia in the back end, and then, obviously JavaScript on the front end. But so there we are. So the back end is built using Dr. Baker's packages with Genie as the model view controller framework. So it all sits on top of that. Very easily, it was very easy to get it up and running. Genie is a blessing for this.
And on the front end, we use JavaScript with React. And the reason we chose React is because you're not really changing pages, you're kind of changing components of when you create these tensor networks. So we found it to be more efficient. And with React, we use the package React Flow. And the reason we use that is React Flow was actually built for like the typical graphs you find in computer science, where you have nodes and edges. And the diagrams for those are quite similar to tensor networks. So we chose to use React Flow for that reason.
So the app has two main components. First of all, an algorithm runner, and then second of all, a tensor network builder to allow users a wide variety of uses. So with the algorithm runner, currently you can run a algorithm called DMRG, Density Matrix Renormalization Group, which is one of the fundamental quantum algorithms for classical computers. It's broke ground, I think, around 30 years ago, and it still is very widely used today. With the full release of DMRjulia, we will be implementing some of the algorithms which Dr. Baker talked about, such as TRG, PEPS, and MERA. And you can also input custom Hamiltonians. So any physical system that you can find in a paper, you can just plug right into this website very easily.
And for the other component we have is the tensor network builder. And the idea is you can build tensor networks, you can run computations on these tensor networks that you've built, and using the output from this, you can use it with the rest of the library, like DMRjulia and 10pack.
So more on the algorithm runner. For this side, here is an example page of it. You have a number of sites. So here we have 8 sites. So that would be, say, 8 electrons in a spin model, and then you would apply some Hamiltonian, your model. Here we have the Heisenberg model selected. You can choose to compute certain correlation functions. You can choose to impose symmetries. It's just basically what this boils down to is there's some simple inputs, and it gives you a simple set of outputs. All of this is done with JuliaCon, where it just feeds the information through to the back end, and it just makes it very easy and efficient. So to run DMRG, you can do this to obtain energies, correlation functions, and then you can also impose quantum symmetries on the problem, and that gives you a whole other set of energies and correlation functions for that altered version. So currently, with this implementation, you can run on some known models from the literature, such as Heisenberg, Hubbard, and TJ, all things with known solutions and which give values you can check against. Then you can also input custom Hamiltonians, as mentioned earlier. So these are just very complex mathematical forms, but basically the entire idea is it would not be fun to figure out how to do this and actually code it up on your own. So this, you just see what it is in a paper, input it on a menu, you have constants, you have, each operator, every single one you need is there, and then the back end connects with DMRjulia, does all the operations, and then gives you whatever observables you wanted, such as an energy or something. Then here's another example, just 6 components, the same for the Heisenberg model. Looks a bit more complicated, but it's all very easy. You just copy what's on the screen or in the equation, and then it's as easy as that, really. It gives you the exact numbers you want.
And so we're coming back to the tensor network builder. And so, as I mentioned before, you can build tensor networks, you can run your own algorithms. It's nice to visualize tensor networks because sometimes when you see it in the code, it's really difficult to figure out, like, what does this actually look like? What am I doing? But here you can see it visually. And for that reason, you actually don't really need any coding background because as you can see, you can drag and drop tensors and connect them, and it'll do it all for you in the back end. And so the output, so what happens is once you're done all your computations, you simply click run network steps, and it'll do all the computations you've done up until that point, and then the output will be the tensors that resulted from the very last computation you did. And so these tensors, you're able to use them with the rest of the library if you need to continue the operations further. Oh. Huh? Oh. Sorry about that. So the operations that you can do include contract, singular value decomposition, QR decomposition, LQ decomposition, and eigenvalue decomposition. And as you can see on the GIF over here, it is doing an eigenvalue decomposition. So currently it is around 2 a.m. in Victoria. So we were unable to have the website public for everyone to use because if it were to crash, if too many people were trying to use it, we don't have any support that's readily available. But when we do release it public, it'll be done using the Digital Research Alliance of Canada resources.
So just to wrap up, in summary, so in order to just to wrap up in summary, these are the download instructions, very simple. We're currently beta testing the version 1.0. Once Julia 1.11 comes out, then we'll be releasing that. And we have the DMR Genie slated for release very soon. So if we just want to say a bit of thanks for the people that are helping us to integrate this into the Digital Research Alliance of Canada, and of course the funding resources, and our beta testers that are making sure that there aren't going to be any problems down the line. So if you have any questions, we'd be happy to take them. Thank you very much for your attention.
Hi, well, thank you for the talk, and also thank you for fitting it in the 20 minutes, so we have plenty of time for questions. I really liked the interface. I think I almost couldn't tell it was Julia, which is maybe great, and then plus the graphical Genie interface was fantastic. But I'm kind of curious, like, under the hood, I can see you're probably using a lot of types to override BLAST operations, and it sounded like you have some custom implementations for tensors and whatnot.
Sure.
Can you talk a little bit about what's going on under the hood?
Yeah, sure. And then maybe I'll hand it off to Aaron and Kiana because they really did the front end. So on the back end, on the underneath side of DMRjulia, it's actually not even using the array type, which is in the base version of the Julia library. You can use the array type if you want to, but at least as a couple of versions ago, and then I never bothered to check because I've essentially. It's almost a very nice branch of Julia that has done some things that are very different on the back end. Right now, at this particular moment, there's a custom struct called a tens type, and it essentially just stores a vector, which we want to replace with the memory incoming, and then something to tell you what the size is. What this prevents, and this just felt like an easier way to program it, is that you're not constantly changing the rank of the tensor. And I felt like this was just something to kind of avoid, and it turned out to be rather quick in order to do this. In terms of what's going on the underneath side, essentially, and I regret that I had to do this in order to make it this fast. But a lot of the functions that you would apply onto the tensor have been completely rewritten. So I think one of the notable ones, and this is a very tiny one, so it's not something to get into a fight about, but the permute dimensions operation in DMRjulia is a little bit faster on average over all the possible permutations in the test that we have in the library, the unit test. So it actually derives some computational benefit to sort of go in and redo everything. I don't know what the status of that array type is at this point. I don't know. I know that there's some other groups that try and look at how to reshape these things and not have a type instability. But yeah, it's almost a complete rewrite of Julia, unfortunately. I wish we could have used some of the things, but we just wanted to avoid the garbage collector at all costs, essentially. That was the... But maybe you can talk a little bit about the back end of what you used for the front end, just to say a little bit about that, because it is. I agree, it is rather impressive what they've put together.
Sorry, what was it in terms of the back end that you wanted to know?
I think your interface is fantastic, and so I just maybe wanted to understand a little bit more what's happening under the hood to make this work.
Yeah, of course. So basically, we use Genie. We built an app. It's just one line to do that with Genie, which makes it very simple. Then we use the model view controller framework. So if you used Ruby on Rails, it's very similar to that. You create some view in HTML, and then you add a route for that. So all the basic things. And that boils down to something that's very nice, I found, is that you can have Julia on the back end in routes or a controller, and you can have a .jl.html file, which allows you to call Julia in HTML and make it very easy. You can just pass variables back and forth. Any data is just streamlined to go from one end to the other, and you really don't have to think at all about what you're doing at that point. It's just very basic, and we couldn't find any alternatives besides Genie that actually allowed you to do that. Then for the JavaScript side, it's a little more complicated. We had to use some JSON and send it back because that's just what we found worked best with React. But yeah, I would say that about sums that up.
Great. Thank you. Did anyone have any other questions?
Apologize for being late, so I might have missed this, but do you guys benchmark DMRjulia against any other packages, maybe even other languages?
Yeah, I used to, just to make sure that I was sort of getting to the point where it was in the realm of being as fast. In scientific computing, as I'm probably sure that some of you at least are aware, there's very notable cases where people get really animated about these things, so I stopped doing that at some point. The story that I can tell is that in the quantum chemistry community, the very first quantum chemistry software that got really big was Gaussian, and that was made by this Nobel Prize winner, John Popple. And then at some point, Popple decided he didn't really want to do this anymore, so he handed it off to a student. And there's a very well-known group of people that have tried to compare their codes against Gaussian, and you get banned from having a Gaussian license. And John Popple got banned from Gaussian. So there was, at one point, a website of people who had been banned from Gaussian. And I used to work on another tensor network library code and wrote documentation and developed things for it. And I just thought, it's, I figured any trick that anybody's playing, it's just going to seep into one code over another. I just wanted to concentrate on the design choices. The last time that I benchmarked it against the codes that I know of and know how to use, it was faster, but who knows, it could have been optimized to some other point. I think the other thing is that those low bond dimension scalings that you often find that people compare against, they don't really matter. Typically the BLAS routines take over. So long as you don't have something going wrong in your Julia code where you have a bunch of allocations, everything's going to scale asymptotically to the same point. So no, out of a courtesy, feel free to compare against. And if you find something that's inefficient, please send a request or get in touch. We're more than, we have no ego. We just want to do good science. This library has a lot of uses in the group. It's a group of 9, so there's a lot of projects going on. And these guys are just the 2 lucky undergrads who pulled this project. So, yeah, but if there's anything that anyone notices, we always invite. I'm getting more and more emails about this, so it is useful if you want to take a look or something like this. Yeah.
Cool, thank you.
Anyone else?
Thank you very much. So you also use this for teaching, you said?
Yeah, I just ran a directed studies class because there's not really any other way for these students to access this. The papers that are out there are pretty pedagogical. They go in step. I don't know. There's like an infamous review of modern physics by Uli Scholach from 2005, and then a follow-up in 2009. These are great papers if you know what reshape is, but typically students coming in do not have this vocabulary, and so everything that's trying to be done here is to get the student to start doing research faster and not leave them kind of hanging. I think at least the groups that I came up in, we were never given code. You had to make everything yourself, which was, or the code was so inscrutable that it wasn't worth trying. And this is kind of like the one of the papers for the DMRG that was sort of just, I wrote it in the pandemic, and it probably needs to be submitted at some point finally, but it's called Build Your Own Tensor Network Library, because it's just like, why not? Why not know how to do the stuff that's going on inside of there? So, yeah.
Yeah, great. Thank you.
Yeah, I can see why you would be interested in Julia 1.11 features, because there's a new memory basic type that array and whatnot are built on, and it sounded like what you were trying to do is a lot of maybe what static arrays does with kind of immutable vectors and array structures. So
yeah, exactly. That's why we wanted to just hold off on the version 1 release until we saw what was going on here. There's some other reasons that we're here. Like I mentioned, if anyone is interested in RISC-V, this is very much in our interest.
And you also mentioned OpenCL, so I was interested in what you were doing with OpenCL that you couldn't do with Julia.
Well, so OpenCL, this is one of the only times that I know when this has happened. The open source standard is just vanishing, which is a very strange concept. I think that just speaks to where NVIDIA is in the market right now. I used to do all the GPU programming in this OpenCL.jl package. And then it didn't work for a long time. And then now it's back, and the line on it is, we're looking for someone to maintain this, and I don't know if I want to do that, but definitely there's some possibilities to speed things up with a GPU in a tensor network context, and that's essentially what we want to do. Just regular matrix multiply and probably some other. I don't think there's a good SVD out there for GPUs. They're just general.
There's a library called I think kernel abstractions, which tries to generalize over different platforms, and it's not like it's in the right direction. I'm not sure if it's capable.
I used to play around with ArrayFire. I don't know if that's still
Yes.
popular now. And like systematically something would break in these things. You'd go over the memory limit. You wouldn't know how to unlimit the memory. The other thing is it's so fast, partly because it's 100% Julia code on the bottom. So there's really it really makes it very fast to download, fast to run, fast to maintain. I'm hesitant to introduce external packages into it at this point.
Right. Great. Thank you.